And then second, we use this triphenylphosphine measurement to try to determine if thermal reversion was the mechanism of aging. And so that's kind of the four-part outline for this, the first part of the talk. Okay. Okay. So we have in this study four tires and 2 lab compounds. Okay. And so there's a new tire. There's what we call a field tire, which was obtained from a driver like you and me, with 7.4 years and 44,000 miles of service in Phoenix, Arizona. And then there was an artificially aged tire. It was in the oven at 60 degrees C for 6 weeks. Maximum sidewall pressure, 42% oxygen, inflation gas. Okay. And then there's a wheel tested tire, 7 days on the road wheel. And this is lab mixed compound, natural rubber, conventional cure, and natural rubber efficient cure, unfilled, aged and unaged for FTIR and for crystallization kinetics. So the first test, so we had dissected the rubber between the steel welds, and we measured crosslink density by swelling. So this is swelling in toluene and then subsequent calculation of the crosslink density using the Flory-Rayner equation. So here's the crosslink density of the new tire, and you can see in each of the aged tires, the crosslink density is higher, artificially aged by running on the road wheel. So the first thing to mention is that running on the road wheel is kind of an expensive test, already at 7 days, and you're not even close to the field. So the use of the road wheel as a way to achieve a field tire is just kind of way too expensive. The oven aged tire was able in a reasonable amount of time to achieve the properties that are seen in a field tire. And so we look at this as a great thing that's happened, because now we have a artificially aged tire and a field tire with the same crosslink density. And so we use these two, to kind of study the details, what's going on. So the first thing we did is crosslink distribution test. And there's a test method reported by MRPRA research group, and Seville and Campbell publication, where they use thiol cleavage agents. They cleave the polysulfidics, and then you do a swelling test, and then the second cleavage agent cleaves the polysulfidics and the disulfidics, and then you do a swelling test, and then by subtraction you can calculate the number of crosslinks that are from the polysulfidic type, the disulfidic type, and anything that doesn't get cleaved by the cleavage agent is called the monosulfidic. Okay. So here's the new tire, the number of polysulfidic crosslinks, the number of disulfidic crosslinks, the number of monosulfidic crosslinks. And then the field tire in red, and then the oven aged tire in yellow, and then the wheel aged tire in light blue. So even though the field tire and the oven age tire have the same crosslink density, all the crosslinks have to show up somewhere in here. But if you notice that most of the crosslinks that are formed in the field tire are found to be quote-unquote polysulfidic type, and most of the crosslinks that are formed in the oven-age tire are monosulfidic type. So they have the same crosslink density, but very different distribution of crosslink types. So we say the aerobic aging of the bilk coat compounds led to increased crosslink densities. Change in the crosslink distribution were followed by wet chemistry, thiol cleavage agents. By this technique, the new crosslinks formed appeared to be either polysulfidic type or monosulfidic type. The formed crosslinks in the field tire were mostly polysulfidic, and during the oven aging, they were mostly monosulfidic. So we say, you know, they're not really polysulfidic and they're not really monosulfidic, but there's some type of chemical structure that show up in this test as having a different chemical structure. So we want to know what the real structure is of these crosslinks that are formed during oxidation. And so the next test that we did is carbon-13 solid state NMR. And here's a typical spectrum. And, you know, carbon-1 is shown here, carbon-2 is shown here, carbon-3 is here, carbon-5 is here, and carbon-4 is here. So here is the vinylic carbons, and here's the allylic carbons. Okay. Now, the whole point of showing you is if you look down in this area, there's a whole bunch of small peaks. And Professor Jack Koenig at Case Western University in Cleveland, Ohio, you know, spent a major portion of his career analyzing these small peaks down here. And so here's an expanded view of that portion of the carbon-13 NMR spectrum. And he identified, these are all carbons that are bonded to a sulfur. And he identified all these peaks and the chemical structure associated with that carbon that's bonded to a sulfur. And, you know, is it a trans C5 and C1? So what we decided to do was we integrated all these small peaks, determine total percentage of carbons that are bonded to a sulfur. And that data is plotted here. This is the percentage of carbons that are bonded to a sulfur atom. Okay, so the new tire, you know, it's 1.4%, and the wheel tested tire, the field tire, the oven age tire, and this is crosslink density. So it shows clearly that the field tire and the oven age tire, you know, we're not increasing the number of percent of carbons that are bonded to a sulfur, you know. So from this data, we say that, you know, no way that, you know, you're driving down the road and continuing vulcanization in your tire, you know. So we say from carbon-13 spectroscopic analysis, no evidence was found for formation of more sulfur crosslinks in the field or the oven age bilk coat compounds. Okay, and the next test, we're trying to determine the polysulfidics. This is triphenylphosphine extractable sulfur, which is a measure of the polysulfidics. The triphenylphosphine will extract sulfur from any sulfur linkage which has 3 or more sulfur atoms. And so this shows you the data of the new tire and the oven age tire, and we say they're not significantly different in this test. So we say triphenylphosphine results of the extractable sulfur measurement in the sulfur network suggests that the original sulfur network stays intact during these aging conditions. No thermal reversion. No evidence of thermal reversion. And so, we're left with oxidation, and then here the next 3 slides are from last week's presentation where we did a service life prediction model based on oxidation kinetics, and we measured integrated oxygen consumption as a function of aging time in a series of temperatures. And using that data, we were able to, develop a prediction curve, which was in very good agreement. So, with all this data, we're saying that the oxidation is able to explain, all of the changes in the crosslink density and the other properties that we see. Okay, so now we're trying to, this is infrared results, and we're trying to determine what's the chemical structure. And so these are, lab mixed compounds, and we have to take the carbon black out in order to get good infrared spectra. So these are unfilled natural rubber, conventional cure, efficient cure, and peroxide cure. And this is the percent change. So this is the percent change in the hydroxyl peak and the percent change in the carbonyl peak. And this peak is associated with sulfoxide, peroxide, ether, and epoxide linkages. And you can see that the conventional cure has a much greater change, than the efficient cure and the peroxide cure. So somehow sulfur is, accelerating the oxidation. And we also see, a cis-trans rearrangement in the conventional cure, which we don't see in the efficient cure and a peroxide cure. So here we show the infrared spectra of the conventional cure before and after aging, 5 weeks at 70 degrees C. And so we see the increase here associated with the hydroxyl group, and then we see the increase here due to the carbonyl. And then we see this broad peak here, which we say is associated with sulfoxide, peroxide, ether, and epoxide linkages. So that is the extent of as far as we were able to go on that subject. So we say by IR spectroscopy, the linkages formed during aerobic aging appear to be oxygenated species, sulfoxide, ether, epoxide, or peroxide. However, the sulfur linkages are probably participating in the formation of crosslinks in the form of sulfoxide. So, my best guess is that the new form linkages are sulfoxide. At higher temperatures, oven aging temperatures, presumably the oxygenated linkages rearrange to carbon-carbon linkages with the evolution of CO2 and SO2 gases. Okay, so the next 4 or 5 slides, you know, very, very, very important. So here is the tensile property of those four compounds, okay, belt coat compounds. So here is the stress strain curve of the new tire, and here's the wheel tested tire. Here's the of an age tire, and here's the field tire. So even though these, you know, have very different, you know, types of crosslinks, you know, it has this, you know, almost the same properties, right? And so we asked the question, you know, this is the unaged and this is the aged. You know, if you're just, all you're doing is putting crosslinks in there, you know, we understand the modulus going up, we understand the elongation to break going down, but why is the strength going down? You know, it's not, you know, if all you do is put more crosslinks in there, it doesn't make sense that the strength is going down so much. So we spent a little bit of time trying to figure out why the strength decreased. What's the mechanism behind? And I don't show it, but sometimes I could have included, but I didn't. We have the crack growth data, okay, and we compare the crack growth data, and of course these have much higher crack growth rates than the unaged, and these two are not significantly different. So even though they have different crosslink types, they have the same tensile properties and the same crack growth properties. Okay. So anyway, the next question we try to answer is why the decrease in the strength? And we said one idea we had was, it's, you know, natural rubber, it's very important for natural rubber to crystallize on stretching. And so we measured the crystallization kinetics of aged and unaged. And so here is the, we stretch the sample, put it into the freezer, and then we measure the force as a function of time. This is a published technique by Professor Alan Gent. And so, you know, as the sample is crystallizing, you see this loss in force measured by your force transducer. And so this is a measure of the ability of this compound to crystallize. And you can see that upon aging, after 1 week, it's crystallizing much slower than the unaged, and then two weeks, and then 3 weeks, and then four weeks, and 5 weeks. Okay, and then this is not our data, but this is data from Professor Juan Valentine in Spain, published in Macromolecules, and this is time domain NMR double quantum experiment. We have the capability of doing these types of experiments. And here it shows the, this is the distribution in molecular weight between crosslinks for the unaged natural rubber conventional cure. And then after 7 days, after 20 days, 50 days, 90 days, 157 days of aging. And so, you know, going from a narrow distribution in molecular weight between crosslinks to a broad distribution in molecular weight between crosslinks during aging. You know, presumably the oxidation reactions start, that may be going faster, on a molecular scale in some regions and slower in other regions. So you don't get a uniform increase in the distribution of molecular weight between crosslinks. So in summary of the first part, we said the crosslinks formed during aerobic aging Belco compound were found to be two types. The following mechanism is proposed to explain the results from the various techniques. Chemical structure of one type is probably sulfoxide, sulfur-oxygen linkages. The second type is probably carbon-carbon linkages. The former was the primary structure, crosslink structure formed during field service. The latter is the primary crosslink structure formed during oven aging. Temperature, presumably, is the key factor governing the structure of the crosslink that is formed. The oven-aged tire belt coat and field service tire belt coat compounds were obtained with the same total crosslink density, differing in crosslink types. Thereby, these two samples provided a comparison of the role of crosslink types formed during aerobic aging on physical properties. By tensile properties and crack growth rate, there was no significant difference between the field and oven-aged belt coat compounds. I mean, a crosslink is a crosslink. If it's a sulfoxide crosslink or a carbon-carbon crosslink, it was performing the same in terms of physical properties. The fundamental mechanism of property decay during aerobic aging was considered by examining crystallization kinetics before and after aging. The crystallization kinetic data suggests that oxidation of natural rubber is associated with loss of crystallizability on stretching. Crystallizability was presumably affected by pendant side groups and cis-trans rearrangements. The network uniformity, distribution, and molecular weight between crosslinks probably was affected, became broader in distribution. This would also deteriorate the mechanical properties. In other words, if you're looking at a non-crystallizing rubber, such as SBR, that, when it's oxidized, it's also associated with increase in modulus, loss of elongation to break, and also a loss in tensile strength. So we would say probably the reason in that case, it's non-crystallizing rubber, is that the network uniformity has been affected. Okay. So this was, a question that came to our mind. That means it seems to us that there's a mechanism change in the oxidation of natural rubber, probably around 40, 50, 60 degrees. And we now have a technique, the crosslink distribution test, to try to quantify and understand that mechanism change. So we said to better understand the mechanism of oxidation of natural rubber compounds at service temperatures, low ambient temperatures, how does it differ from elevated temperatures used, for our accelerated aging tests? And so we, have this outline, or this test plan. Okay. So first, just talk about the motivation and background for this project, and then our hypothesis. And that the test plan is room temperature and oven aging at 4 temperatures: room temperature, 37 degrees, 45 degrees, and 70 degrees. And the testing include tensile, DMA, strain sweeps, and our cross-link distribution wet chemistry thiol cleavage agent technique. And then we also did what we called temperature cycling. So we're going to try to understand the mechanism change, which we think we see around 40 or 50 degrees C. And so the next 3 or 4 slides are background or motivation. So these are the empirical shift factors from elongation to break and ultrasensitive oxygen consumption, which we talked about last week. This is data on a different compound than the one we talked about last week, but it is a natural rubber compound. And the elongation to break data and the CO2 generation, the carbon monoxide generation fall on this line. But if you look closely, the oxygen consumption rate data is following non-Arrhenius behavior. And somewhere around 50 degrees C appears to be a mechanism change in this natural rubber compound. And this is true for most elastomers. And there's one catastrophic example that's given where it was wire and cable example, and they did the elongation to break data, and then they extrapolated down to ambient temperature, and they buried miles and miles of wire and cable, and they had predicted 100 years service life. But actually that compound deviated, and you can see, it almost 10 times. So instead of being a 100-year life prediction, it should have been a 10-year life prediction. And so after 10 years, they had to dig up all that underground wire and cable. And this has been published for other elastomer systems, butyl rubber, and NBR, chloroprene. This is the work of Ken Gillen at Sandia National Laboratories. Sandia National Laboratories developed the ultrasensitive oxygen consumption technique to enable them to better predict, service life of military things. And my understanding is that the service life is often governed by an O-ring seal in military missiles. So it's very important to know how long it's safe to store those things. Okay. So here is another example of natural rubber compound, and there's the difference is the AO loading, antioxidant loading, and this shows the oxygen consumption rate shift factors for no antioxidant, kind of falls on the Arrhenius line. But if you look closely at low temperature, the one with the antioxidant at 1.25 pHr loading, and the compound with antioxidant loading at 2.5 pHr are deviating and exhibiting some non-Arrhenius behavior down at the low temperature. And this is shown in more detail here, where this is the oxygen consumption rate as a function of aging time, 21, 30, 45, 60, and 80. And if you look at the 80-degree data, you know, the compound with no antioxidant is oxidizing, you know, significantly faster than the compound with 2.5 PHR. The expected, you know, we would expect the compound with no antioxidant to be oxidizing faster than the compound with antioxidant. However, if you look down at the 21 degrees C data, the compound with 2.5 PHR antioxidant, kind of the purple circles, is oxidizing faster than, you know, the 20 than the compound with zero antioxidant. So it seems like, you know, there's a mechanism shift, right? When you go from 80 degrees to 21 degrees, you know, in the middle, you know, they're kind of the same, you know, oxidizing at the same rate, you know. So there's kind of a shift, you know. And then here we show the integrated oxygen consumption again, you know, at the 80 degrees C, zero antioxidant is aging faster, oxidizing faster than the no antioxidant, the expected ranking. But at low temperature, we're seeing the opposite, where the one with 2.5 PHR of antioxidant, the blue circles, is oxidizing faster than the compound with no antioxidant. Okay, so and then just one more slide here. So two more slides here associated with the background. So these are the two tires: the new tire, the field tire, the oven age tire, which we described earlier. And here's the Crosslink density results that we talked about earlier: the new tire, field tire, oven age tire. And then here's the Crosslink distribution of those three tires, with the formed crosslinks showing up as polysulfidic for the field tire, and the new crosslinks formed during oxidation in the oven age tire showing up primarily as monosulfidic types. We say the compound is not forming polysulfidic crosslinks, but rather a type of crosslink with an oxidized chemical structure that is observed as a poly. Okay, so the hypothesis is between 25 degrees and 65 degrees C, there is a change in oxidation mechanism. The change may be a subtle change. However, now we have a technique that is able to detect the change in mechanism. We decided to explore this. Okay, so the test plan is of oven aging at 4 temperatures: room temperature, 37 degrees, 45 degrees, and 70 degrees. And the testing included tensile, DMA strain sweeps, and crosslink distribution using the thiol cleavage agent technique. And then we also, in the end, I'll describe experiment we call temperature cycling. So we, you know, lab mix these two compounds. This is natural rubber conventional cure with unfilled, and then here's a lab mix conventional cure with carbon black filler. So we have unfilled and filled model compounds. Okay, so here's the tensile results of the filled compounds before and after aging: 70 degrees, 45 degrees, 37 degrees, and 21 degrees. So here's the unaged, one day, 21 day, five weeks. And then here unaged, 7 day, 25 day. And then we have unaged, 2.5 months, 8 months. And then room temperature, you know, unaged, 1 month, 2.3 years. And then here's the tensile results for the unfilled compound: 70, 45, 37, 21. Here's the unaged, one day, 5 week, 21 day, and then 45 degrees unaged. And then we have 7 day, 25 day, 67 day. 37, we have unaged, 2.5 months, 8 months. And then unaged and 2.3 years. Okay, so you know, for mechanism study, we use the Arrhenius technique, right? So here is the we have the rate of decay and elongation to break, and this is the rate of increase in the modulus at 100%. And you know, going from 21 degrees to 70 degrees, we see, you know, no evidence for a change in the mechanism. And then if we look at the modulus, you know, going from 21 degrees C to 70 degrees C, no evidence for change in the mechanism of aging. And here's the unfilled, decay and elongation to break, plotted on a Arrhenius plot. Rate of increase in M100 plotted on a Arrhenius plot. Both cases, no evidence of a mechanism change around 40 or 50 degrees centigrade. Okay, so here's our DMA results of the filled compound. So here's the unaged, you know, 1 day, 21 day, 5 week. And then so on for 45 degrees, 37 degrees, and 21 degrees. So we looked at the low strain modulus. So we took, I think we used the modulus at 0.1% as our metric. And then here's our DMA results for the unfilled compounds. And so here's unaged, 1 day, 5 day, 21 day, 5 week. And then here's the data for 45 degrees and 21 degrees. And here's our Arrhenius plots for increase in modulus at 0.1% for the filled compounds. And here's the rate of modulus increase at 0.1%, plot an Arrhenius plot for the unfilled compound. And again, we see no evidence of mechanism change. Okay, so here is our Crosslink distribution test results. Here is the total Crosslink density. Here's the polysulfidic, number of polysulfidic crosslinks, and then I combine the monosulfidic and disulfidic So this is the rate of crosslink formation. This is the rate of polysulfidic crosslink formation, and here's the rate of mono and di crosslink formation. And it's plotted on Arrhenius plot, and we see no evidence of a mechanism change. We plot total crosslink density. But if you look at the polysulfidic and the mono plus disulfidic, we see evidence, for mechanism change around 50 degrees centigrade. The rate of formation of polysulfidic is falling on nonlinear, non-Arrhenius, and the formation of monosulfidic is falling on a non-Arrhenius behavior. And then here is our unfilled compound, total crosslink density, polysulfidic crosslink formation, mono and disulfidic crosslink formation, plotted Arrhenius style. The total, we see no evidence for non-Arrhenius behavior or mechanism change, but we see that in the polysulfidic, and we see it in the mono-disulfidic crosslink type measurement, where there's a change in mechanism around 50 degrees centigrade. Okay, so this is just a one-off experiment. So we said to ourselves, if at low temperature you're forming sulfoxide and peroxide, and at high temperature you're forming carbon-carbon crosslinks, we decided to do what we call temperature cycling. So this says a 9-day aged at 80 degrees C. And so the one, there's sample without temperature cycling and with temperature cycling. Without temperature cycling means it was in the oven at 80 degrees C for 9 days. With temperature cycling means every day it comes out of the oven. So it's in the oven for 1 day, out of the oven for 1 day, in the oven for 1 day, out of the oven. So, it's an 18-day experiment to generate a nine day with temperature cycling. And we hypothesized that with temperature cycling would age faster, because you're forming peroxides, and then you put it back in the oven, the peroxides will quickly break down. And so we expected with temperature cycling to be lower. Here we use energy to break. Next week we'll see what sometimes there's advantages to use energy to break in place of elongation to break. So energy to break is the integrated area under the stress strain curve. So we're predicting this to be lower, at every aging time, but we can, yes, it's low, significantly lower here, but it's actually significantly higher here. Here, no difference. And then again, here it's significantly lower. So we said this idea didn't work. I mean, that wasn't a valid idea. Okay, so in summary and conclusion of this second half, we say there is a mechanism change between 40 and 60 degrees in natural rubber. And I would say in most other elastomer compounds, it's fairly, more stronger and easier to detect, but it was very elusive and hard to detect with natural rubber. We used both filled and unfilled And this was detected only by the crosslink distribution test, polysulfidic crosslinks and diamonosulfidic crosslink, formation rate. The chemical structure of the crosslinks formed at low temperature, below 40 degrees C, was predominantly polysulfidic. The crosslink type, the crosslink can be broken by a thiol cleavage agent. This is not actually a polysulfidic crosslink. It is probably peroxide or sulfoxide. Chemical structure of the crosslink formed during intermediate temperature, 40 to 60 degrees, have a combination of two types of structures. The predominant chemical structure of the crosslinks formed at high temperature, above 60 degrees, are probably carbon-carbon crosslink structure. Other techniques, physical testing techniques such as tensile properties and DMA properties, were not able to detect a change in mechanism. Although the chemical structures of the formed crosslinks differ with temperature, they exhibit the same properties. So it's actually a very nice conclusion. You can do your accelerated oven aging and measure the properties, and understand that those properties are the same properties if they were aged for longer time at lower temperature. Okay, and then the last slide here is I just kind of mention the agenda for next week. So we're under the title of rubber aging. And I thought that I would try to cover these four topics, if you agree. So I say two mechanism aging, when we have both oxidation and thermal reversion present. And then secondly, the effect of strain on oxidation, bridge bearing or footwear, or, if it's, is it aging faster because of the strain that is under and experiences? Effect of antioxidant loading on service life prediction. And then we also did this study on NBR, HNBR, and FKM compounds for oil and gas exploration. And the major test that they use for that is called rapid gas decompression. So we looked at the damage mechanism during downhole oil and gas, rapid gas decompression testing. This paper is open for questions.
Right. Thank you so much, Dr. Terrill, for such a wonderful presentation. We have
You're welcome. Thank you.
We have a couple of questions, so I will
Good.
put it across to you. The question is, in real life, there are a lot of other factors which influence the degradation, like UV zone.
Yes.
So the question is, how accurate is this model? And if a customer asks for warranty of the product, how we define this warranty period? What is the time deviation from the actual versus the predicted?
So this is how I try to handle that. I don't have a lot of experience, but if you remember last week, we had that issue with partial pressure was not atmospheric, and there's a duty cycle, and so we identified a shift factor in the oxygen consumption rate data to account for that. So what I'm hoping to do, in future studies is to, we have clear glass, oxygen consumption reactors, and put the reactor into the UV chamber, right? And so we can get the change in oxidation rate associated with the UV exposure versus the consumption rate without UV exposure and get a shift factor. The other idea that I'm hoping to try is, measure tensile properties, at the same temperature, but with and without UV exposure, and get a shift factor. Of course, the more temperatures you do that, the better, your confidence in your shift factor. And there's also some recent publications by Ken Gillen. He's actually retired, but he recently was able to actually with some of his coworkers that are still there in the lab, do a joint publication, and they were looking at the effect of it's kind of wire and cable application in I forget it's a plant that has radiation exposure. So he published. I know he gave a paper at the last ACS Rubber Division meeting, and he's published it. So there, he works out the mathematics or the analysis for when you have a radiation in combination, with oxidation. So that's where I am. I mean, you you have oxidation and UV that you need to try to account for.
All right. So the next question is, does the crosslink density get influenced by the types of sulfur donors like TMTD factorized with temperature? And what should be the test conditions for crosslink density?
The oxidation rate is significantly affected by the sulfur content in the compound. The higher the sulfur content in the compound, the faster it oxidizes. So I think that the sulfur, is somehow participating in the oxidation mechanism. It reacts faster than the carbon, so to speak. And as far as the I don't know if you were asking about the chemical structures. I don't really chemical structures. Presumably there's similar between efficient cure and the conventional cure, but definitely the conventional cure will be oxidizing faster than the efficient cure.
Right. So the next question is there any difference in crosslink density distribution in the filled reinforcing and non-reinforcing fillers like CaCO3?
I did that study with and without carbon black. We don't see any difference there. If you go to a different filler type, I don't as far as I know, I don't think the filler is going to affect the kinetics and crosslink types. I think let's see what I guess if you have high filler loading and low filler loading, one with I mean, if you would, basically, if you reduce your polymer content, I think, you'll slow down your oxidation a small amount.
All right. Uh, how to remove skim from a field tire? This is one question which is being asked.
Yes, so it's not easy. So there's about a millimeter of rubber, and it takes a long time and kind of someone that's willing to, uh, use it's a scalpel blade, and strong people with strong fingers to try to extract that rubber. And then, of course, you need to make it smooth on both sides. If you have any knife cuts, of course, you won't get good tensile properties. So you got to put it on. We put on a kind of a grinding, make a very smooth surface on the test specimen, so you can get good tensile properties.
All right. The next question is how to construct a Arrhenius analysis graph chart.
Yeah.
And what level of R square is required to make the judgment?
Yeah. So radius plots are really, really helpful. I mean, that's how you do kinetics and mechanism, right? It's how everybody does it. So I think the thing that was so revealing to me, you can do it on any metric, DMA properties, tensile properties. And so, you just, and there's a couple ways to do it. One is to use log time, and the other one is to use the log of the rate. Right? And I think it's almost like you have to do it yourself. I mean, just kind of make up some data and practice doing it. It's not easy, so to speak. So as far as the R squared, so I mean, the more data points it helps you. When you have the elongation to break and you have the ultra sensitive oxygen. So the more data points you have, the stronger your R squared. So I mean, you kind of need a good R squared, 0.85 or better, just to be able to see these differences in mechanism.
All right. So the last question would be, if the thickness of skim CPD is millimeter, then how to check the tensile strength?
Yes. So for the tensile test, we use this we call mini dumbbell. It's a dumbbell. It's about two inches. It's an ASTM. I think they call it type 5. And because it's using the grinder and to try to get uniform thickness and smooth surface. You're really happy. If you 3 inches by 2 inches. So we use the smaller dumbbell, and I mean, if you got a 1 millimeter thick and smooth on both sides, you'll get good tensile properties. Yeah.
All right. So another question which has come up right now is, for aging test, there are 4 temperature levels given. So what is the recommended time bound to get the optimized properties to conclude?
So in the last study, we used 4 temperatures. So how many temperatures do you recommend? Is that make sure I understand the question? Maybe read the question again, Mansur.
Right. So the question is, for aging test, there are
Yeah.
4 temperature levels given. Now, what is your recommendation? So what is the recommended time bound to get the optimized properties to conclude?
So, um, you know, I'd like to refer back to last week, if you don't. So last week, I think we used 6 temperatures for the ultra-sensitive oxygen consumption and 4 temperatures for the, the oven aging tensile properties. That kind of is the way I think. Of course, you have time constraints or cost constraints. You reduce that, when not necessary. But if I were you, I would try to, think about, 6 temperatures for your ultra-sensitive oxygen consumption and 4 temperatures for your tensile properties.
All right. So these are the questions which we had for today.
Okay.
And I would request everyone, if you have any questions, you please do write to us. We will get your answers from Dr. Ed Terrill. And thank you so much for joining today. We look forward to have you again with us in the next session, which is on 16th of October, which is
Mansoor,
on
thank
rubber
you.
aging agenda, right?
I hope it was helpful.
Yeah,
Thank you,
sure.
Mansoor.
Thank you so much. Thank you so much for joining us.